Hello students, today we will discuss boundary layer theory introduction. So let's start.
So, the concept of boundary layer was first introduced by Prandtl in 1904. When a real fluid, that is the viscous fluid, flows past on a stationary solid boundary, a layer of fluid which comes in contact with the boundary surface of the solid body adheres to it due to the viscosity, and condition of no slip occurs. Thus, the layer of fluid which cannot slip away from the boundary surface undergoes retardation. This retarded layer further causes retardation of the adjacent layer of the fluid, thereby developing a small region immediate vicinity of the boundary surface, in which the velocity of the flowing fluid increases rapidly from zero at a boundary surface and approaches the velocity of mainstream or free stream velocity. To understand boundary layers, let's try to understand this. Suppose a free stream velocity of fluid with a velocity capital U is coming from this side, and this is your solid boundary surface. When this fluid strike here, which is called leading edge, this is called trailing edge, here at in every distance of x you will get a imaginary point where the velocity at this point is 99% the velocity of mainstream velocity, and it will increase like this way. And if this point can be connected by using one line, then it is called boundary layer. So in the boundary layer you will get inside boundary layer, outside boundary layer. So in the outside boundary layer the velocities are, basically velocity is mainstream velocity, but inside boundary layers from the bottom it is 0 and it will increase, and at this point the velocity here is 99% the velocity of mainstream velocity, and this is called boundary layer thickness. So here the region inside the boundary layer is viscous shear stress takes place, and region outside boundary layer where the flow behavior is quite like a ideal fluid, and potential flow theory is applicable. So here what happened, since this velocity increases from 0 and at this point it became 99.9% of mainstream velocity. So here you will get a velocity gradient. Velocity gradient is not equal to 0. But outside the boundary layer the velocity gradient is 0. So if velocity gradient is not equal to 0, so if you apply Newton's law, of viscosity del u by del vi. So this is not equal to 0. In the sense your tau is not equal to 0. Here this is equal to 0 in outside, so tau is equal to 0. So inside the boundary layer, you will get relative velocity. You will get relative velocity between the layers. So when the layer of the velocity moving in y direction, then what happened? The molecules also rotate in their own axis. So inside boundary layer, the flow is rotational, but outside is irrotational. If outside is irrotational, then you can say your vorticity is equal to 0 or omega is equal to 0. And if you observe from the leading towards this direction of x, the thickness of the boundary layer is increasing. Why it is increasing? Because from the outside, from this direction, rate of mass flow increases along x direction. That's why the thickness of the boundary layer increases along x direction. So a few characteristics of a boundary layer. The thickness of boundary layer increases as the distance from the leading edge, that is x, increases. This one increases, this boundary layer increases. Thickness of the boundary layer decreases as mainstream velocity increases. If mainstream velocity increases, the thickness is also decreased. Thickness of the boundary layer increases as kinematic viscosity increases. Kinetic viscosity of the fluid. When a mainstream velocity u increases in the downward direction, boundary layer growth reduces. When a mainstream velocity u decreases in the downward direction, flow near the boundary is further retarded, and boundary layer growth is faster, and it is susceptible to a separation of boundary layers. If mainstream velocity decreases, then separation of boundary layers may occur in the surface of the body. So next one, if ux kinematic divided by kinematic velocity, x is the distance of the from the leading edge for a flat surface, is less than 5 into 10 to the power 5, the boundary layer is laminar and velocity profile is parabolic in nature. If ux by kinematic viscosity is greater than or equal to 5 into 10 to the power 5, then the boundary layer is turbulent and velocity profile is logarithmic or power law. And if this value ux divided by mu fall between these two, then it is called transition. The critical value of ux by mu at which boundary layer changes from laminar to turbulent depends upon few factors like turbulence in the ambient flow, surface of the roughness of the body, pressure gradient, plate curvature, temperature difference between the fluid and the boundary. So this is one diagram This is your leading edge, this is your trailing edge, this is your, suppose, the solid surface. So a free stream of fluid is coming from this direction with a velocity capital U, suppose, and after striking here you will get a boundary layer, and this is transition, this is turbulent flow. So you get a boundary layer like this. So if the mass flow from the outside of the boundary layer increases, then thickness of the boundary layer also increases. And at a certain point, it is shown in the figure here, the velocity profile for this boundary layer is parabolic. That means it is a laminar boundary layer. And if you go beyond that, you will get a logarithmic in nature boundary layer where the delta, which represents thickness of the boundary, is increases. So boundary layer thickness is defined as that the distance from the boundary in which velocity reaches 99% of the velocity of the mainstream. 99% of the velocity of the mainstream. It is denoted by delta. So your delta is a function of x. This is your x distance. This is your y. So at this point, this is your delta, and if you go along with the x direction, along with the on a leading edge to trailing edge, so boundary layer thickness increases. Why it is increases? Because there will be a mass flow from the outside of the boundary layer. I hope you understand the introductory part of the boundary layer. In the next class, we discuss other terminology. Thank you. Stay safe.